Let's continue with our JiTickLogic library. Hello everyone, this is Ali Reza. Welcome to the Mentor Code Lab. In previous episodes, we had implemented our Blackboard, the tree, the node, and we already had implemented 4 important nodes: the start, the action, condition, and sequence. In this video, we will work on our selector node. A selector node is a node that will tick its own children in order. The difference compared to sequence is that the moment one of the nodes returns success, the selector will become success. So in these examples, for example, if a sequence under the selector returns failure, that's okay. The selector will go for the second branch. If this selector returns failure, that is when the whole tree returns failure, and then the selector will become failure. Compared to sequence, we can say that sequence is somewhat close to AND conditions. Everything should tick successful so that it will become successful. A selector is more like OR condition. When one true comes out, the OR is true. So if one of the nodes return true, or success in this case, the selector will return success and it will not tick the rest of its own children. To write the code, it's actually close to what we have compared to sequence. The design is a little bit different when it comes to the logic. So we have a node, selector node, and again we will have the generics, and it's an I composite. Again, the same deal. So implement the tick and let's talk about what we have. As I said, we will have lots of copy paste from here. So we will have index and running children, and we will have constructor matching super, and in this case we are not accepting any param, so just like that. Okay, here we just call the super. No, we don't need null, we are calling the parameterless constructor. Then we will have another constructor that accepts the Blackboard like so. And did I add it here? Yes. So I didn't add this guy because it was simple enough, but I should have added here because as we talked in the previous episode, we may have a condition on the super without the calling here. We may have problems later. So this guy is actually calling the super on the parameterless, and here is correctly assigned. Okay, so a selector much close to this guy. So you see that I will do a copy paste here and we will start talking. So if the running child is equals to, it shouldn't be null, and that was a logic error that we had in the previous episode. So if we are not null, then we want to track the running child. And finally, when we are doing the while, we get the child result, and then we get the status of the child. Now, here is the thing. If it's failed, we will change it. If it's success, then we return success because that's where everything is done. If it's running, then we do the same thing. Otherwise, we increment the index. At the end, when we got here, we failed because that's the logic there. Let's review it. We have many childs, and as we said, the selector needs only one successful node. So if it's success, then set the success and return. If any node is running, then we assign the running thing and then increment. So at the end here, we made sure that every children were ticked and all of them failed, because if one of them were successful, we already broke out of the loop. So here we made sure that every child was failed, and this is only the time that we return failed for selector. Believe it or not, this is all the logic for a selector node. So we will go for parallel node. Now, parallel node is different from both nodes. If I have an example of a parallel here, now parallel node doesn't care what specific node was failed or succeeded. All it cares is that how many of these nodes were successful or failed. And based on that count, it will make a decision. So when you tick a parallel node, it will tick every one of these nodes regardless of their status. Then it will collect the number of successful and the number of failures, and at the end it will make the decision that, you know what, 80% of the nodes were successful, so I'm successful. That's the job of parallel node. Now, in reality, when you go to something like C++ or C#, when you have the concept of multi-threading, a parallel node should tick each and every one of the nodes in parallel in different threads so that it gathers everything as fast as possible. So the second node shouldn't wait for the first node to finish. They will execute at the same time, and only when every one of them return their status, then the parallel node will collect collect the number and make the decision. However, in here, we can't do it in multi-threading. Honestly, I'm not sure how multi-threading is working in Minecraft itself, and I'm not sure about the multi-threading in Java itself. I never used it. I want to be safe, and in case of Minecraft, honestly, I don't see a very practical use case for parallel node. However, for the sake of simplicity, we need to add the parallel node. Anyway, let's have a Java class parallel node. And again, we want the generic section. Now, parallel node is another composite, so we will mark it as composite. And now, if I go back to the node class, or I'm not sure if it was the start node, I think it was the node class that had this parallel node. That fixes that error, and here we are checking if the node is a child of a parallel node. So we check the parent instance of parallel. Sometimes it can be useful. So let's take a look at our start node. Here we are not handling the parallel separately. Actually, we are not doing anything with that check and that method. However, it's a good thing to have because parallel node is, as I said, a little bit different compared to other nodes. And here we want an integer as success threshold and a list of statuses for the returned statuses of our nodes. So a list of tick status for children statuses. Then we have a constructor that is parameterless and it asks for the success threshold. So here we will call the super so that we initialize and then we assign the success threshold. Then we have another constructor that accepts the blackboard and success threshold. Okay. After that, in both cases, we need to instantiate that list, new array list of nothing, and this tick status here is redundant. So now we made sure that we have instantiated our list and we accepted the threshold. Finally, in our tick logic, we will say int success count equals to 0, int running count equals to 0. Then we say if child statuses dot is empty, we want to say for I equals to 0 and smaller than children dot size, and we say child statuses dot add children at I. Actually, no, we are initializing it right now. So we say it's status failure. So we preemptively make sure that every child status is failed by default. And this is a one-liner, so I will remove these. Then we say, again, for another I less than children.size, here we say node t child equals to get the child at I if children status dot get at index I does not equal to tick status dot success. So if we didn't tick it before, okay, then we want, actually, it will never happen. Now that I think, oh, no. Okay. I will talk about it in a few minutes. So let's say that tick status equals to child dot tick. Then we say child statuses dot set at I with the status. Then if status equals to running, then we want to say running count plus plus. Take note, here we are not adding ourselves as a running node to parent. That's not job of a parallel. That's a main difference between parallel and sequence and selector here. Then outside of the loop, we say if success count plus running count is greater or equal to threshold, then we say if the tree does not equal to null, then we want to say tree.add running node this. Now here is when we are assigning ourselves as running. However, here's the situation. It can be success on all the nodes and the running node will be 0 and it will get beyond the threshold. So why should we set ourselves as running again? So here I need to check and running count is greater than 0. So if we have a running child, then we want to do that. Oh, wait, I did mess things up. Before this, we say if success count is greater or equal to success threshold, then we say return success. Otherwise, if this is happening, now here's the thing, running count can be 0, okay? And this wouldn't have happened. So if running count is 0, this wouldn't have happened. If success count is less than threshold, but adding the running count makes it equal to threshold, means that we are running actually. Yes, that's true now. We don't need to check it here. And finally, we return the running status. Then here we say at the very end, return the failure. Because at this point, we made sure that the success count is not enough and we are not actually having a running count that makes us running status. And at the end, we just say we are failed. So that is it. This is happening inside the for loop. It shouldn't happen there. It should happen outside of the for loop. Now I want something. You remember that we had this reset method and so far it had done nothing. But here we clear our list. Now, why did I struggle on this thing and said that it will never happen? I thought that we are preemptively initializing every child status to be failed. So here I was thinking like, okay, the child status is already failed, so this will fail. This is just all the time. It's not success. However, I forgot that we are checking for the emptiness. If the child status is not empty, means that in the previous tick, we had a running state and some children were successful. So at that time, we will not happen inside this if statement. Then we come back here and we check if the result was not success. So either we were running or failed. At that time, we will tick that child. Okay. We reevaluate the failures again here because as I said, the parallel doesn't care about the results. It just needs to collect the result. So now that is working and this is the correct logic. And the reset happens when we want to retick the whole tree. And if I go back inside logic tree, at the start of the tick, we see that we say start node.tick and the start node.tick is checking if the running node is empty, then it will tick the first node. Now here's the thing. We are not calling the reset here. And that's something. I assumed that the logic class, the logic tick class, the one that is sitting inside behavior tree, would reset the whole tree. Now, if running nodes are empty, means that we already ticked the whole tree and we are not busy anymore. So at this stage, we may want to say this.tree.reset. And of course, we may want to check if the tree is null or not. Actually, it can't be null. I think it can't be null because when we are setting the nodes, the start node or the root node or whatever it is, we make sure that the start node knows that we are the tree. So that is it, because recursively it will set the tree for every node. So normally the tree shouldn't be null at all times. So anytime that we are doing this, it's really meaningless. However, the reason for these sanity checks is that, let me comment this single line and you see that it's not harming anyone. So why bother? Because if at any point the tree becomes null, means that we had done something wrong. And I want to have that exception. So why should I handle that and make sure that I'm bypassing it? So anytime that I'm checking the tree does not equal null, I will remove it. This has a potential to cause exceptions, but as I said, that's a wanted exception. I don't want to bypass that possible extension situation. So inside our condition, it's okay, and action is actually not okay. So that's it. Anyways, back to our parallel node. That's all we want to do. So in the reset call, happens at the start of the tree when we have no running state. We clear the list so that in the tick, it will reinitialize the child statuses and then it handles everything. Okay. Now this is the parallel node and let's take a look at our list. We already finished these. I will bypass the subtree for time being and I already had done the parallel node. Now the next node that I want to talk about is actually until success and until failure, and a node that I don't have here, and I will add many nodes after these in the application and get the, I would call it 1.1 anyway, and those will be the random node and some nodes related to Minecraft. However, for time being, I think I will go for until success and until failure. I will pass these two for time being. I will pass the subtree for time being because I want to have the easier ones first, and then we will go into a random node, and then we will revisit random selector and random sequence, and after them we will have our subtree node, and then we will go for dedicated nodes that we may have inside Minecraft.
If you like these videos, please subscribe to the channel, hit the like button and turn on that bell so that when I publish a new video, you will get informed. Have fun everyone. Bye.